A paper published 2 weeks ago in Nature Astronomy might have just made the search for alien life a whole lot lonelier, and not for the reason you'd expect. For decades, the big question in planet hunting has been simple. Is there liquid water? If a rocky planet orbits at just the right distance from its star, not too hot, not too cold, we call it habitable. That's the famous Goldilocks zone. It's the foundation of everything we do when we look for life out there. And it sounds reasonable, right? Water is the universal solvent. Life needs it. Find the water, find the life. But what if water isn't enough? What if a planet can sit perfectly in that zone, have oceans, have a nice temperature, have everything seemingly going for it, and still be completely, permanently, biochemically dead? Not because something went wrong later, but because something went wrong before the planet even finished forming. That's the argument this new study makes. And the numbers behind it are uncomfortable. A team led by Craig Walton at ETH Zurich in the University of Cambridge published a study showing that there's a hidden chemical filter that most rocky planets probably fail. And this filter has nothing to do with distance from a star. It has nothing to do with whether a planet has an atmosphere or a magnetic field or plate tectonics. It goes deeper than all of that. It goes all the way down to the core. Literally. Let me explain what they found, because the mechanism is surprisingly elegant. When a rocky planet forms, it goes through a phase where the whole thing is basically molten, a giant ball of liquid rock and metal, a magma ocean. During this phase, iron sinks to the center and forms the core, and silicate rock floats above it and becomes the mantle. That separation, core from mantle, is one of the most important events in a planet's life, and it happens early. We're talking the first 10 to 100 million years. Now here's what most people don't think about. When that iron sinks, it doesn't go alone. It drags other elements with it. And which elements get dragged down depends on one thing: the oxygen conditions in that magma ocean. Geochemists call this oxygen fugacity. It's basically a measure of how much oxygen is available to participate in chemical reactions in the melt. Not oxygen gas like you breathe, but oxygen locked up in minerals and compounds, thermodynamically available. And this single parameter, this one dial, determines whether a planet gets to keep two ingredients that are absolutely essential for life as we know it: phosphorus and nitrogen. Now, why these two? Phosphorus is the backbone of DNA. It's the backbone of RNA. It's the energy currency of every cell, ATP. Without phosphorus, there is no genetic code, no metabolism, no life. Nitrogen is in every amino acid, every protein, every nucleic acid. You can't build biology without it. And here's the problem. Phosphorus and nitrogen behave in opposite ways when a planet's core forms. If the oxygen conditions are low, what geochemists call reducing conditions, phosphorus bonds with iron. It becomes what they call siderophile, iron-loving. It sinks into the core, gone, permanently locked away, biologically unreachable. Meanwhile, under those same reducing conditions, nitrogen stays in the mantle. Plenty of nitrogen, but no phosphorus. Flip it the other way. If oxygen conditions are high, oxidizing conditions, phosphorus stays in the mantle just fine. But nitrogen becomes volatile, escapes into the atmosphere, and can be lost to space over time. Lots of phosphorus, but no nitrogen. You see the trap. You need both. And both are only available together in a narrow window. The team calls it the chemical Goldilocks zone. And how narrow is this window? This is the part that really matters. Across the range of plausible oxygen conditions for rocky planets, the amount of phosphorus in a planet's mantle swings by a factor of 100,000. 5 orders of magnitude. That's not a gentle slope. That's a cliff, a small shift on the oxygen dial, and your planet goes from having enough phosphorus for an entire biosphere to having almost none. At the low end, their model shows mantle phosphorus dropping to less than 1 part per million. Earth has about 100. That's 100 times less than what Earth has. And Earth needed every bit of that to get life started. Now, Earth formed at a specific spot on this oxygen scale, about 2 logarithmic units below what's called the iron-wustite buffer. That sounds technical, but the point is simple. Earth hit the sweet spot. Both phosphorus and nitrogen were retained in the mantle in useful amounts. Not too much of one, not too little of the other. And everything that followed, every bacterium, every fish, every tree, every person watching this, all of it traces back to that chemical setting being correct during the first 100 million years of Earth's existence. 4.5 billion years ago, before there was an ocean, before there was an atmosphere worth mentioning, before anything even remotely alive existed, the planet's fate was essentially sealed. The kitchen was stocked. Or, for most planets out there, it wasn't. Let's look at our own solar system through this lens because it's revealing. Mars formed at slightly more oxidizing conditions than Earth, and the model predicts exactly what we see. Mars has plenty of phosphorus in its rocks. Rovers have confirmed that, but it's nitrogen poor. Mars failed the chemical Goldilocks test on the nitrogen side. Now, Mars has plenty of other problems: the thin atmosphere, the lack of a magnetic field, the freezing temperatures. But even if you magically fixed all of those, this study suggests Mars might still have been chemically handicapped from birth. It never had enough nitrogen. Mercury is the extreme case on the other end. Incredibly reducing conditions. Almost all of its phosphorus would have been dragged into the core as iron phosphide. Mercury was, in the language of this paper, chemically doomed from the start. Venus is interesting. It probably formed under similar oxygen conditions to Earth, which means it might actually sit inside the chemical Goldilocks zone. Venus's problem isn't its chemistry, it's the runaway greenhouse effect that turned it into a furnace afterward. So the chemical Goldilocks zone is necessary for life, but clearly not sufficient. You still need everything else to go right too. And then there's Enceladus, Saturn's little ice moon. And this is where the story gets a twist that actually brings some hope back in. Enceladus probably never went through significant core mantle differentiation. It doesn't have a big iron core. So the whole mechanism this paper describes, the one that strips phosphorus away, it just doesn't apply. Phosphorus stays dissolved in Enceladus's subsurface ocean, and Cassini actually detected phosphorus there, along with all the other elements life needs: carbon, hydrogen, nitrogen, oxygen, sulfur, all 6 of them in liquid water, with chemical energy sources. So while this paper narrows the odds for rocky planets orbiting in habitable zones, ocean moons like Enceladus and possibly Europa sidestep the filter entirely. They play by different rules. But back to the big picture, because the implications for the search for life are significant. The team combined their chemical Goldilocks zone with existing estimates for how many planets are in the traditional habitable zone and how many are Earth-sized. And when you stack all 3 requirements together, water zone, right size, and right chemistry, the numbers get harsh. They estimate you might need to survey thousands of otherwise Earth-like planets before you find one that actually passes all 3 tests. And there's data to back up the chemistry side. When researchers look at the chemical compositions of nearby stars, which approximate the raw materials their planets form from, fewer than half appear to have the right compositions to produce planets in the chemical Goldilocks zone. That's before you even ask about orbital distance or planet size. This connects to something bigger that a lot of people have wondered about: the Fermi Paradox. If the universe is so vast and so old, where is everyone? Why haven't we detected signals from other civilizations? This paper doesn't claim to solve the Fermi Paradox, but it does add a new, quantitatively sharp filter to the list of reasons why habitable planets might be far rarer than we thought. And there's a specific angle here that's worth thinking about. In the framework people use to talk about existential risk, there's this concept called the Great Filter, something in the chain from dead matter to spacefaring civilization that is extraordinarily unlikely. If the filter is behind us, great. We already passed it. If it's ahead of us, that's terrifying, because it means civilizations tend to destroy themselves before spreading through the galaxy. This chemical Goldilocks zone operates at what you might call step 0, before life even begins. If this is a major filter, and the 5 orders of magnitude swing in phosphorus suggests it's a pretty sharp one, then that's actually good news. It means we might have already won the hardest lottery. The filter is behind us. The hard part wasn't building civilization. The hard part was being on a planet that had the right ingredients in the first place. Now let me be honest about where this study has weaknesses, because it absolutely does. First, this is a model, not an observation. No one has measured the phosphorus content of an exoplanet's mantle. The team used a simplified, single-stage core formation model. Earth almost certainly formed through a more complex, multi-stage process over tens of millions of years. The authors are upfront about this. They argue the effects they're seeing are so large, 5 orders of magnitude, that model simplifications don't change the fundamental conclusion. And that's probably fair. But the exact boundaries of the chemical Goldilocks zone could shift when more complex models are applied. Second, the nitrogen side is messier than the phosphorus side. Their model actually overestimates Earth's mantle nitrogen by about a factor of 10. They attribute this to atmospheric loss processes they didn't model, which means nitrogen's behavior is less well-constrained and the real window might be even narrower than they calculated. Or it might be that post-formation processes like impacts and atmospheric evolution modify the picture in ways that loosen the constraints. Third, and this is important, there's an interesting tension with another line of evidence. When astronomers study polluted white dwarfs that have accreted rocky debris, they can actually measure the chemistry of that debris. And a 2019 study found that all 12 extrasolar rocky bodies examined had oxygen conditions consistent with our own solar system's range. If Earth-like oxidation states are common, then the chemical Goldilocks zone might not be as exclusive as this paper suggests. That's an unresolved tension. Fourth, this study only considers life as we know it, carbon-based, requiring phosphorus and nitrogen. There's been speculation about alternative biochemistries, arsenic instead of phosphorus, for instance, though that's never been confirmed. The authors acknowledge this limitation. We only have one example of life, so building your model around that example is reasonable. But it's worth remembering that the universe might have more imagination than we do. And fifth, there's a potential escape hatch the paper itself mentions. Phosphorus and nitrogen can be delivered after core formation by meteorites, comets, and cosmic dust. Late delivery. If that delivery is significant enough, it could partially compensate for a planet that started out with the wrong chemistry. There's even research suggesting that fine-grained cosmic dust could concentrate on ocean surfaces and act as a kind of fertilizer for prebiotic chemistry. So the chemical Goldilocks zone might not be an absolute wall, more like a very high bar that some planets could still clear through external help. So where does all this leave us? We've spent 30 years telling ourselves that the universe must be teeming with life because there are so many planets in habitable zones, billions in our galaxy alone. This paper doesn't say life is impossible elsewhere, but it says the menu of genuinely promising worlds is probably much shorter than we assumed. Having water isn't enough. You also need your planet's internal chemistry to have been set correctly during a brief window 4.5 billion years ago. A window that most planets apparently miss. And the practical impact is real. Right now, telescope time is precious. James Webb, the upcoming Habitable Worlds Observatory, planned for the 2040s. Which planets do you point them at? This research says you should be looking at stars that are chemically similar to our Sun. Stars whose compositions suggest their planets could have formed in the chemical Goldilocks zone. It's not just about finding planets in the water zone anymore. It's about finding planets that had the right ingredients from the beginning. The traditional Goldilocks zone was about location. This is a Goldilocks zone about identity. Not where a planet is, but what it's made of. What happened inside it before anything could live on it. 4.5 billion years ago, molten iron sank through a magma ocean on a nameless young world. As it fell, it left behind just enough phosphorus and just enough nitrogen in the rock above. That rock became Earth's mantle. That mantle became the crust. That crust weathered and released those nutrients into oceans where they were gathered up by the first molecular machines that could copy themselves. Every living thing on this planet is downstream of that moment. And according to this study, that moment almost didn't happen. Shift the oxygen dial a little in either direction, and you get a world with oceans, with sunlight, with all the right temperatures and absolutely nothing alive. A beautiful, sterile rock. We might be rarer than we ever imagined, not because of where we are, but because of what we're made of. If you want to keep up with discoveries like this one, the kind that quietly reshape how we understand our place out here, there's always something new waiting.